Besides the X-bar and R charts we saw earlier, depending on the type of data we have, we might need to plot a slightly different kind of control chart. The X-bar and R charts are applicable for process measurements that are called variable measurements. You can think about variable measurements as things that are measured, such as length, weight, temperature, miles per gallon, etc. Another kind of measurement is an attribute measurement. You can think about attribute measurements as things that are counted rather than measured, such as number of defects, number of customer complaints, etc. These measurements are also of the yes-no type. Let us say I am interested in keeping track of another aspect of my coffee machine. After my employee hits the green button, the machine takes a while to brew the coffee. Often, while the machine is brewing, my employee rushes over to the baked goods shelf to get the customer a donut, etc., and quickly gets back before the machine is done. Sometimes, however, the employee gets delayed, so the coffee begins to cool down. Such delays happen on average once out of every 20 times. I want to monitor these delays and make sure this aspect of the process is behaving normally. If the number of delays increases abnormally, my customer satisfaction levels could be affected. Here I am measuring a yes-no attribute. Either my employee is on time or is delayed. Rather than watch the employee all the time, once again I am going to take a random sample of 40 customer orders throughout the day. In this sample, on average, I expect to find 2 delays. But I do also expect that there will be some range within which this number normally varies. In this case, the measurement I have is a proportion. This kind of data follows a binomial distribution, and the appropriate chart to plot is a p-chart. Given that on average, a delay happens once out of 20 times, the average proportion delayed, or p-bar, is 0.05. This p-bar will be the center line of my control chart. The standard deviation of this proportion, sigma p, can be calculated using the formula shown. Once I know the standard deviation, I can calculate the UCL and LCL as the mean plus or minus 3 standard deviations. Note here that the proportion must always be between 0 and 1. Of course, I cannot have a negative number of delays, so I can truncate the LCL at 0. Likewise, I also want to keep track of another aspect of my coffee machine. The water in the tank is automatically preheated to a certain temperature, which ensures a more consistent temperature of the brewed coffee. But I have found that if my employees brew 4 or more cups in quick succession, the preheated water runs out, and an alarm light goes on. In an average day, I have noticed that the alarm light goes on 8 times, which is to be expected given the sudden surges in customers that we experience. However, some days the alarm light goes on 12 to 15 times. Is that normal? A change in the alarm pattern might indicate that either my employee is not following proper procedure, or there is some change in the demand pattern. Either way, I want to know. Here also I am measuring a yes-no attribute. Either the alarm light goes on or it doesn't. But suppose I know that the light went on 12 times today. Do I know how many times it did not go on? I have no idea how many times the light tried to go on, but said, "Oh, forget it," and went back to sleep. So I have a count, but not a proportion. This kind of data follows a Poisson distribution, and the appropriate chart to plot is a C-chart. Given that on average the light goes on 8 times a day, the average count, or C-bar, is 8. This C-bar will be the center line of my control chart. The standard deviation of this count, sigma c, can be calculated using the formula shown. Once I know the standard deviation, I can calculate the UCL and LCL as the mean plus or minus 3 standard deviations. I cannot have a fraction of an alarm, so I truncate the UCL at 16. I cannot also have a negative number of alarms, so I truncate the LCL at 0.